Hi everyone, we're here today to talk about Condy, NestMates, and Constable, understanding some of the JDK11 and 12 JVM features. These are the features that modify the JVM specification, and they're some of the smaller features that don't get noticed as often when we're talking about new Java releases. And these features are actually really important because they're building blocks for things that are going to come in the future. So I work for IBM, so of course I have a large safe harbor slide. Basically, don't believe the things I'm going to tell you, even though they're all about features that are open source and have already been released. So, all right, so who am I? I'm Dan Hedinga. I work for IBM, as I said. I've been involved in virtual machine development for about 12 years now, working on originally IBM's J9 JVM and now on the Eclipse Open J9 JVM. And over the years, I've done a bunch of things throughout Java, being able to touch on pieces like JSR292, the Invokedynamic bytecode, and then following on with that with Lambda, and then a number of the other projects like Project Valhalla since then. And it's been really interesting to see how some of these features have evolved from things that were focused on dynamic languages to things that are more available and more broadly used throughout Java. So before we get too deep into this talk, I want to jump back to something that was mentioned in the keynote about the faster release cadence, meaning smaller features. With the move to these 6-month releases, we're getting smaller things more regularly. So if we look back, Java 8 had Lambda expressions. And so when that was delivered, you got Lambdas themselves, you got extension methods, you got the streams APIs, you got new APIs and collections. And it's a really big thing touching all kinds of pieces and really easy to say, wow, that's a big headline feature. With the smaller release cadence, we're seeing pieces of things being carved off to be delivered earlier so that down the line, they're available for some of those more interesting, larger, more user-visible features. But the benefit is that they're now available for you, particularly if you like generating bytecode, right now. All right, so if we look at JDK11, there are sort of two major features that affected the JVM specification. Nest-based access control, or NestMates, and I always get the name of this one wrong, dynamic class file constants, or Condy. So these are the two that we're going to take a look at, even though JDK11 was released September of last year. All right, so NestMates. Let's start by looking at this feature. And the piece we want to look at is a very simple class here. Right? We have a class A, and inside it is an inner class. That inner class has a private int member of name f. And then the enclosing class has a test method that creates a new instance of the inner class and reads the field. Right? This is very straightforward code. People have been writing this kind of code for years and years and years, ever since inner classes were introduced to the Java language. So why are we talking about it when we talk about Java 11? Well, when we look at the bytecode for this, we see something that's kind of surprising. The bytecode does what we'd expect the light gray bytecode basically doing the object initialization. And the bytecode that I've bolded here is a little bit surprising. When we get a field in bytecode, we expect to see a get field bytecode. Instead, we're seeing this invoke static, so calling a static method that doesn't occur in the source of my application anywhere. And it's got a particularly obtuse name, $inner, which is the syntax for referring to inner classes in Java bytecode, and then the name is access $000. So what is this and where did it come from? So what we have, though, is an access bridge. If we look at the bytecode here, up in the top corner there, you see it's doing that get field that we were expecting. So why did we have to introduce a method to be able to do the get field that's that simple, straightforward bytecode that we wanted? And why is this method tagged as ACC synthetic? So this method comes about because we need some way to bridge from what Java, the language's view of accessibility is to the JVM's view of what accessibility is. This is typically referred to as the translation strategy, and it covers how Java-C and other compilers take your source code and map it into bytecode. And generally, when looking at the translation strategy, we really like that to be fairly straightforward. So you look at the source, you have a pretty good idea of what the bytecode's going to become. And this doesn't fit that. Why? The reason for this is the JVM and the Java language don't align on the accessibility rules. So I've put up the rules from a post-modularity spec, which basically says that public access is within your module or within other modules that have read access to the packages you've exported. Package access is what you'd expect if you're inside the same package. Protected says if you're inside the same package or a subclass. And private is where this difference shows up. The JVM spec says you have to be in the same class to have access to a private member. The language says if you're in the same class or a nested class. Oh, there's that word, nest. So, okay, there's a little bit of pain in the translation strategy. Java-C had to generate a little bit of extra bytecode. Why do we care? Well, we got these access bridges, and they mess with that straightforward mental model of mapping source to bytecode that we know and love. And it introduces this extra layer of wrapping. So you've got extra bytecode there. It takes a little bit more memory. Probably not a lot. Probably not something you really notice. It's something you have to invoke instead of doing a field access, so it's a little bit more work for the JIT. Again, probably not a big deal. But the place where it starts to show up and cause problems for people is in reflection. When reflection runs, it uses the VM's view of accessibility, not the languages. So let's take a look at reflective access. Here we've got another really simple inner-outer class example, this time using a private void hello method on the inner class. And then I'm creating an instance of my outer class, creating an inner instance of my inner class, and calling that method. This will again generate an access bridge to allow the method to call to proceed. Now, this is straightforward, but what if I wanted to instead do it with reflection? Right, so I've looked up the method reflectively, and then I go to invoke it. Does anybody know what happens here? It doesn't work. You get this wonderful exception. Legal access exception. The outer class cannot access a member of class outer $inner with modifiers private. So this is a corner case that most people don't hit very often, but when you do, it's a giant pain. Right? You have to go back and modify something to remove the private from it, widening access in places you don't want to, or you have to pull out the set accessible hammer and go make this available. Again, not great answers. So what can we do? Well, we'll start by defining nests. And at this point, it should be a pretty obvious definition given the examples we've shown. A nest is a set of classes that are defined together. And this makes sense from a programmer's perspective. You've written those classes in one source file. You'd really like them to be treated as one thing by the JVM and by the language. So here we have class A, which is the nest host, and we've got 3 classes nested inside it, B, C, and D. Now we need some way to take this information and give it to the VM, so the VM knows at runtime that these things were defined inside each other. The attributes we have up till now are not sufficient to validate that relationship. So in Java 11, we introduced 2 new attributes, the NestMates attributes. So class A has a nest members attribute, and this is an attribute that it has that defines all the classes that are members or defined inside of it, are part of its nest. So for class A, it would list B, C, and D. Each of B, C, and D are members of that nest. So they need some way to say, that's my nest host. And so that's the nest host attribute. And this allows a bidirectional check. So these classes are compiled together, and they all believe that they are part of the same nest. So when the VM goes to check if private access is allowed, it can check this attribute and say, all right, are you members of the same nest? And does your nest actually believe that you're part of it? This allows the VM to allow that private access that the Java language allows, and allows us to remove a bunch of those access bridges. I will note for people doing JVM TI agents that once these classes are loaded, you can't modify these attributes. JVM TI will fail your class modification at that point. And like any new attributes in the bytecode, we tend to expose them with reflective APIs. Reflection, of course, being the way to view sort of the class file data at runtime. And so there's an API to get your nest host, to get your nest members, and to check member access. And these are required because we've used them to be able to update method handles lookup and reflection to say, are these accesses allowed and acceptable at runtime? So we've actually removed an entire class of bugs here by introducing these NestMate attributes. You'll no longer get those illegal access things where the Java language would have allowed you to have access. Right, so as I said, it removes a whole class of reflection-related corner cases from your program. You don't have to worry about that bug anymore because the VM spec and the language spec now agree on what access means. It's got an added benefit of enabling invoke virtual and invoke interface to target these private methods. Prior to JDK11, you typically had to use invoke special to target private methods. And now we've said, look, inside of a nest, we don't know if the method you're calling in another nest member is going to be public or private at the time you call it. So to preserve binary compatibility, we had to extend the things that invoke virtual and invoke interface can do. This is actually good for everybody generating bytecode because you no longer have to do those checks for are you private or not. And actually, surprisingly, this was the piece of the feature that's the hardest to implement in the JVM. I don't have time in this talk to go into why that's the case, but if you're interested, I'll be around the IBM booth after and we can go over why that's so difficult. All right, so that's cool. We've got NestMates, and I said NestMates are fixing this class of bugs, removing some technical debt. But there are areas where you really want to be able to add to that nest dynamically. The primary example of this is people using unsafe.define anonymous class. You get to define something that acts as though it's a member of another class. And that's a great technique for trusted code, and so we'd like to be able to standardize that in a more usable way. And so we're looking at the idea of dynamic NestMates in some future Java release. All right, so that's NestMates. We made generating bytecode easier, cleaned up some technical debt in the JVM. Let's take a look at ConstantDynamic. All right, so ConstantDynamic is looking much more at the future and at other ways of creating dynamic constants. Now, everybody likes to poke fun at ConstantDynamic because the terms seem to be a bit of an oxymoron, but the truth is that it's really just a dynamically generated constant. Okay, to understand ConstantDynamic, though, we have to understand Invokedynamic. How many people have looked at Invokedynamic in the past? Okay, I see some hands. Anybody generated bytecode for doing that? Okay, so let's run through a bit of a refresher on Invokedynamic, because once we understand that, ConstantDynamic is very much the same thing. So we start here with an Invokedynamic bytecode, and that Invokedynamic bytecode has a constant pool entry of type Invokedynamic. That constant pool entry has an index, that 0, which is an index into the bootstrap methods attribute. It also has a name and a signature, like any other invoke bytecode. And then if we look at that bootstrap methods attribute, that's a piece of Java code defined as a method handle that you're going to run to do the resolution for this bytecode. And there's some static arguments that you can pass if you want to allow defining what's going to happen at this particular call site. So the first time we run this bytecode, it's unresolved. So the JVM has to resolve it. Now, most bytecodes, or most of the other invoke bytecodes, have particular rules on how that resolution happens. And it's very tightly defined in the JVM spec. You know, you look in yourself, you look in your parent, you look elsewhere, and if you find something, blah, 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 you throw exceptions in these cases. Invokedynamic really says, it's up to you. You get to pick what's going to happen. You have your bootstrap method, and we run that. So we run your bootstrap method. In this case, it's the Lambda meta factory, which is the bootstrap method used by Lambda expressions. So we run that, and it goes off and computes and figures out what method you actually want to call. And then it returns an object called a CallSite. That's a reified view of what this Invokedynamic instruction is. It gives you an object on the Java heap that you can talk to, you can work with, you can modify if you need to. That gives you a pointer and for the JVM to hold on to be able to complete your call. And that CallSite points at a method handle. And then once that resolution completes, we become permanently linked to that CallSite. Now, there are different kinds of CallSites, so you can change the target method handle if you want, but this is the basic workflow. You run your Invokedynamic, there's some bootstrap method, it returns a CallSite and a method handle. All right, great. Java 7 gave us everything we need to do anything we want, because now we've got this resolution magic that we can hand off to user code, and you can use it as a Swiss Army knife for pretty much any feature you want. Why do you need anything else? Well, we added it primarily for dynamic languages, because in the Java 7 timeframe, dynamic languages were struggling a bit because they either had to use reflection, which tended to be slow to look up what they were going to call at each call site, or they generated a huge amount of code at each call site to do that lookup. And so you'd have to try to inline through this, and you'd have this huge wad of code that you typically didn't use, and it would throw off your inlining heuristics. What Invokedynamic does is it takes that wad of code that tries to figure out what you're trying to call, and it moves it out of line somewhere else, so that the JIT's able to see this sort of direct path to the method you really want to send. Gives us great JIT performance for dynamic languages. But at the time, we looked at this, and we almost went in a slightly different direction. And that was to say, rather than doing calls, we could do constants. Right? Once we have a bootstrapping mechanism, some mechanism to do an up call and let Java code decide what to return, you can implement calls in terms of bootstrapped constants or constants in terms of bootstrapped calls. And there was a proposal for the expert group to try to do that. But we said, look, calls is really where the dynamic languages community is focused, so we'll do that first. OK, so if we've got calls, why would we want to do constants? Well, we're going to start at the bottom of this slide. So I have some constant that I want to return at some point. And so to do that, I have to wrap that in a method handle. OK, so I've now added one garbage object to hold on to my constant. And there's some level of invocation overhead because I have to now call through a method to get my constant, at least until the JIT comes along and inlines through it. And then I need a second garbage object because I need this CallSite to be able to hold on to that method handle, right? Because that's required by Invokedynamic. And then the bootstrap method has to do some kind of interning because you really want your constants to be constant. And so it needs to have some kind of interning pool or some way to know that when you're asking for this constant, it's giving you back the same thing. And there's a fair bit of overhead here to be able to get from the Invokedynamic you're writing to the constant you actually want in your application. So JDK11 said, OK, let's go back and revisit our decision around constants and provide that functionality. So what does it look like? Well, it looks an awful lot like Invokedynamic. The difference here is that we have an LDC, or load constant bytecode, and it refers to a constant pool type of ConstantDynamic, which has a very similar structure to the constant Invokedynamic used by Indy. Here we see the difference being that it uses a field reference or a single class type instead of a signature. And it follows the exact same process. We start out unresolved. We run a bootstrap method. In this case, one of the particular bootstrap methods that was introduced in 11 to make writing these things easy. This one is the constant bootstraps helper for doing primitive classes. And we return, in my case, this class object that I've been able to bootstrap and become permanently linked. No CallSite, no method handle. All right, so Condy and Indy look an awful lot the same. What I'm showing on this slide is bootstrap methods for both of them. The top one is the bootstrap method using the constant bootstraps for a Condy, and the bottom one is one for an Indy. And we see they both have a lookup object. This is your capability to do lookups, to find methods, to find fields. They take a name or a string parameter. The difference being starting to show up here where the Condy takes a class. This is the type of your constant. The VM is going to validate that the constant you return is actually of that type. And for a Indy, it returns a method type. This is the signature for your method. Right, so we've removed a bunch of the overhead, no CallSite, no target method handle, and we've made these constants be usable in all kinds of other places. So you can use them for Invokedynamic bytecodes, you can use them for LDC bytecodes, but you can also use them as bootstrap method arguments. So you can have dynamic constants that depend on other dynamic constants, which starts to provide a way to do meta programming in the constant pool. I will point out one important difference between Condy and Indy, and that has to do with resolution state. If you've generated Invokedynamics, you're probably aware of the fact that every Invokedynamic bytecode, even if it refers to the same constant pool entry, has unique resolution status. This is different than every other bytecode in the JVM, where the resolution status for a constant pool entry is shared across everybody who talks to it, which provides an opportunity to do less resolution when you're dealing with Condy. So what can we do with Condy and the JDK? Well, we're hoping to see the same kind of renaissance for constants as we've seen with dynamic languages for Invokedynamic. In particular, we have a bunch of constants that you can't encode in the constant pool today. You can't encode null. You can't encode enum constants. You can't encode primitive types, or the mirrors, sorry, int.class, boolean.class, that kind of thing, or VarHandles. In order to do that before, you had to come up with some kind of string-based encoding to tell your bootstrap method what you wanted, and these things tended to be ugly and kind of hard to process. And now we've got the ability to do a much better version of this with Condy. And JDK developers said these are the kinds of things we actually need for the features we're looking at providing in the future. And so there's a bunch of bootstrap methods in the JDK that provide these helpers, right? There's a null constant, one for primitive class, enum constants, looking up static final fields, invoking other method handles, and then looking up VarHandles. So there's a lot of helpers and convenience bootstrap methods provided in the JDK in a class called JavaLang constant bootstraps. Now, generally when we introduce new features, we try to give some guidance on how to use them and warn people about some of the places where things can fall down. And so Condy is no different. If you're going to use Condy, I strongly suggest using the constant bootstraps that come with the JDK whenever possible. These are ones that the JDK developers have written for you. It makes it much easier to provide a common language and common understanding of what Condys are going to do. And they're probably the most efficient way to do the lookups because they've been tuned and used by a lot of people. We'll also see that these bootstrap methods have benefits in Constable as well and tie-ins there. We're starting to see these building blocks as they build on top of each other, building up to larger and more interesting features. If you do need to write your own bootstrap method, it's important to make it idempotent. So there's a certain amount of races that can occur when trying to invoke or trying to resolve a Condy. And your bootstrap method really shouldn't depend on how many times that it's called. It should really be independent of that. So you want to make sure that it takes into account any racy resolution. It doesn't do some kind of counter and return that, so that you're aware because these races can occur between different threads trying to access the same constant. Now, I just want to expand on that a little bit, because the races aren't only within a single method. They're also within any use of that constant. Because Condy has the shared resolution status, that same constant pool entry, if you use it in this method for LDC and you use it as an argument to a bootstrap method somewhere else, those two resolutions can race. Another practice that is helpful is to use the name of the constant to help identify what you're trying to do. So in the first case, the name is Z, which is the bytecode name for the Boolean class. And as you see, the bootstrap method there is a constant bootstraps that's going to look up a primitive class. And so the name tells me, oh, this is going to give you back boolean.class. The second example is one that shows a Condy bootstrap that I wrote, and it returns the mathematical constant pi. By using a name that's meaningful, you make it a lot easier to understand the intent of the code as you're reading through it, and you make life a little easier for your service engineers. All right, so where can things go wrong when you start generating code with Condy? The first one is to make note that you're not allowed any direct cycles when you're dealing with Condys. Condy cannot depend on itself in its own bootstrap methods. Interestingly, though, you are allowed indirect cycles. So if, when trying to resolve your Condy, you call a method that also tries to resolve your Condy, that's allowed. Unless you've done some defensive coding against that use case, you're going to hit a Stack Overflow. But you can do this, and you can actually recover from that if you're careful. But the first resolution that completes is the one that will be permanently installed for that Condy. The other thing to be aware of is that constant pool entries have the same life cycle as the class that they're defined in. So if you stick something in the constant pool, it's going to live for as long as your class. Your class is going to live for as long as its class loader. So if you have a constant from another class loader, you've effectively tied the life cycle of these two class loaders together. So you need to be careful about doing this if you want your class loaders to be unloadable later, unless they're always going to live the same length of time. This is sort of similar to some of the class loader leaks that we've seen people cause with thread context class loaders, except those are recoverable because you can always null them out, whereas with a constant pool entry, you can't. So be thinking class initialization type deadlocks for Condy as well, because the init status is very similar. All right, so that's some practices and pitfalls. Where can we go with this? Well, there's some really simple things that are coming hopefully soon, and then some further in the future things that are coming as well. Right off the bat, the obvious one is Lambda expressions. There's a lot of Lambda expressions that don't capture any state, and it would be really convenient if we could use Condy for them, because there would be fewer resolutions there and a little less memory used to resolve these things. So there is a bug tracking the progress on this. I believe the current state is looking at some performance regressions when they've turned this on. So hopefully in the near future we'll get this, and we'll get slightly cheaper Lambda expressions. How many people have written code like this to avoid initialization loops? Anybody? As part of bringing the JVM up, it's not uncommon to need something now that's not available until later, and it depends on something needed now. And so you end up with these loops where you're not able to load code, and so you end up tucking it away in a garbage class that you're only going to reference later so that you can delay the initialization until it's going to work. Condy is going to become a major helper for this kind of lazy initialization. If you're generating bytecode, you can use it today, but hopefully we're going to see features in the Java language in the future that allow you to generate Condy directly. In particular, there's a JEP tracking this. It's JEP 303, and it's intrinsics for LDC and Invokedynamic instructions. And that JEP will build on Condy to be able to provide interesting features like lazy evaluation and lazy initialization. When Java 9 came out, it added VarHandles. And one of the best practices at the time was to initialize your VarHandles in static final fields. Look them up once, root them in a static final so the JIT can optimize its way through that, and so that you've got them when you need them. Now, that hits you at startup, right? You've initialized your class, you have to go off and load a bunch of these VarHandles, especially for the cases where you're not going to use all of them. Well, Condy allows us to use the constant bootstrap helpers in the VM to be able to root these things in the constant pool instead of in static finals, and to be able to delay that initialization until you actually need them. So we're starting to build up features that interconnect more and more. So VarHandles came in 9. It's a better way to get access to more interesting access modes for fields, atomic access, lazy sets and things like that, compare and set. And now we're getting constant bootstraps to make it easy to use with Condy, and then there'll be newer features building on that to make it easy to express this in the Java language. We're getting this steady stream of small pieces building up together. All right, so that was JDK11. It gives us NestMates paying off some technical debt, and Condy some down payments on future innovation. Let's take a look at 12. So the major feature from a JVM specification point of view is Constable. And Constable didn't actually modify the JVM spec, but it really builds the building block for something that's going to tie into the JVM spec in the future. So let's take a little bit of a look at how the JVM talks about constants. So Java code is actually quite dynamic. All of the things that Java uses are resolved at runtime. And the way we do this is we have a bunch of constants in the constant pool. Constant strings, constant method types, constant classes, constant integers, and they're all symbolic or nominal. And the VM has to do something to take those names and those strings and turn them into things that you can actually use in your program. So this is typically the JVM's resolution, right? Take a look in the JVM spec. There's a bunch of rules on how you resolve any given constant. And what you get out of it is usually an object pointer or a primitive value. And these resolutions occur naturally as part of running LDC bytecodes, as part of running Condys and indies to resolve those bootstrap methods. Now, then your program actually gets some kind of object in the heap, right? So we started with names. The VM resolved it into pointers or values, and then it exposes it as objects to you, right? And so this is the path that things take. And so anytime you want to encode information into the constant pool, you have to use one of these types that the VM's able to express, and then you can resolve all the way through it and get some object that you can operate on in your program. But when we look at this, we see something that looks like a 4x4 grid, and there's sort of this empty block. And whenever you see an empty block, JVM engineers like to find something to fill it. And in this case, what we filled it with is a new class called ConstantDescriptor. It's in the JavaLang constant package. And this is a symbolic version of the information on the heap. So we could see each piece of these reflected down, right? On one side, we've got the objects and the object pointers, that resolved value. On the other side, we have the symbolic information. Now, how do we get one of these constant descriptors? Well, we take any of the things that are constants that could be symbolically created by the VM, and we say, please describe yourself as a constable. Now, what's a constable? Well, Constable is an interface that was added to all of these classes so you can figure out which ones support this kind of transition from an object to symbolic information. And so now I can start with symbolic information, and I can go all the way around to symbolic information. Not very exciting. The reason this is interesting, though, is it starts to give a common language to people doing bytecode generation and to people who want to be able to talk about symbolic information on the Java heap. Instead of having to come up with your own language and me come up with my own language and somebody else come up with their own language, there's now a common description for these types of information in the JDK. right? And we can take that symbolic constant and we can turn it back into a resolved actual live value again by asking it to resolve the constant descriptor. And when we do that, we have to pass in a method handles lookup. The reason for that is a method handles lookup is your capability or your privileges to do lookup on things. And so by using that object here, we've extended that to say, look, if you have the ability to get a privileged lookup of some kind, you can look up whatever that class would have been able to resolve. And so we can go back and forth from constant descriptions to the constants as need be. So what does this actually look like when you want to write the code? This is the example of what a constant description would look like for a Condy. In this particular case, I'm going to create a dynamic constant descriptor. And each of these constant descriptors are a subclass of the overall const descriptor class. So you can find them all easily by taking a look at the Java doc. There's one for class, there's one for string, there's one for method type. And each of them will have an of method on it. And this is the standard method for trying to create one of these things. And so what I'm showing here is a Condy that's using a bootstrap method that we defined in constant bootstraps. It's using that same primitive class bootstrap method. It's passing in I for the int.class. And then it's using this other helper on the constant descriptors helper class to say, hey, this thing is going to return a class. And so we're starting to see tie-ins across these features again. We're seeing Condy, which introduced dynamic constants and a bunch of helper bootstrap methods in constant bootstraps. We're seeing constant descriptors, which has a bunch of helper methods and helper constants to be able to refer to all of the bootstrap methods from constant bootstraps. Right, and then we can resolve this, and this would do the equivalent of running your bootstrap method. Now, what's interesting here is this starts to build a language to be able to talk about constants in the VM for things that you can generate and tie back across. But not only can you do that, you can also canonicalize them. So what I showed on this slide is a bootstrap method for a Condy that knows how to give you back int.class. There's a much cheaper operation that knows how to do that, and that's LDC of int.class. And so that's what this does. It says of canonical. It says, hey, look, there are these bootstrap methods over here that the JVM knows about, and so it can simplify those expressions for you so that when you start to use this language to drive your bytecode generation, you're then going to get the simplest, smallest representation. All right, so why is this interesting? Right, it seems like an awful lot of code to be able to talk about a symbolic constant. And the answer, again, is in JEP303, when you start to be able to express these things in Java code. Today, there's no way to write a Condy in Java. By building up this set of building blocks, when JEP303 lands, you now have this language for being able to do that. And so you can do all kinds of interesting tricks from Java code that build on top of LDC expressions and on top of Condys and indies and things like that. So where are we looking to take this? Well, I showed a loop earlier that started in the symbolic, went through the resolved, and all the way up to get to the symbolic again. What we're looking at doing is introducing bootstrap methods that go from the symbolic straight to the symbolic. So you don't actually have to resolve these things, which means that your meta language for symbols now doesn't have to be only things that actually exist and are resolvable. It can be whatever kind of information you want to encode there. You can now pass it up through constants that may only be describable or resolvable in some other case. So we're starting to bring a deeper level of metaprogramming into the constant pool with some of these new features. So as I mentioned earlier, JEP303 describes how you can use this for LDC and for Invokedynamic. And there's a really cool talk that Brian Getz gave at the JVM Languages Summit in 2018 called Below the Fold, where he takes a similar example to what I've shown here, but then he shows how JEP303 will be able to take that and boil that down into the bytecode that you actually wanted and throw away all of this other code that you had to write to get there. So check that out if you've got an opportunity. That's where this is all going. Right? So when we talk about this smaller release cadence, allowing us to fix up some of the smaller pieces and to start delivering value incrementally, there will be big payoffs in the future, but we start to benefit today. So what do we have? NestMates paid off some of the interclass technical debt. Condy, added dynamic constants, making some down payments on future innovation. And Constable brings that symbolic language to Java users so you can start to do more interesting things. So those are the three major features that we added in JDK11 and 12 that touch on the JVM spec and are sort of down payments on future innovation. If you want to check these things out, drop by the Adopt Open JDK project to download your JDK or whatever vendor you're using to get the JDK from. My preference is always, because I'm an OpenJ9 guy, to grab the OpenJ9 ones. But hopefully that was interesting to all of you. Any questions? Okay, thanks everybody.